Okay, so let's see another kind of machine learning algorithm, the reinforcement learning. Previously, we have seen two kinds of machine learning algorithm. We have seen some based on supervised learning. With supervised learning, we need labeled data, which means that we need for each input the real output, the corresponding output that will be used by the system to learn by calculating the error between the predicted output and the real output. So this is a reason why we need to know the output for this training data. On another kind of machine learning algorithm, which is the unsupervised learning. With unsupervised learning, here we have only input data, but we don't have the corresponding output. This is what we call unlabeled data. So with this kind of algorithm, the goal of this type of machine learning, unsupervised learning, is to generate clusters of similar data. But now we will see the reinforcement learning, which is the third kind of machine learning algorithm. On here, the system which will learn will have to act on its environment to get by itself its own training data. So here, for the two first machine learning algorithms, it's a human which gives labeled data or unlabeled data. But for the third, for this one, for the reinforcement learning, this is a system which will get its own training data. So let's see some examples of machine learning, of reinforcement learning, excuse me. So the first one is with a cart pole. So we have, the goal is to have this stick vertical. So at the beginning, the system performs some commands, left or right, but it doesn't succeed. Okay? If we wait later, the system learns to move left and right quickly to try to move the stick. Later, after some trial, the system learn to balance on. After a few moments, the system learned to move faster to have the stick vertical. Then now, for 180 trials, the system performs to move the stick and maintain the stick vertically. And at the end, it managed to put the stick vertically, even if human do some perturbation. Like this. Okay, so all this was learned by reinforcement learning. Another use of reinforcement learning is in 2016, when AlphaGo, software AlphaGo, defeat the world champion Lee Sedol by 4-1 to the game of Go. The game of Go is something which is very, very difficult to do. And the software managed to defeat the world champion by using the reinforcement learning technique. Now, another example is the use of reinforcement learning to control a tokamak. So what is a tokamak? A tokamak is a big engine, something big like this. which is used to maintain what we call a plasma, hydrogen plasma, to init a fusion nuclear reaction. So because it is very, very hot, it's more than the inside of the sun, it's millions of degrees of temperature. This plasma mustn't touch the wall of the tokamak. So to be sure that it doesn't touch the wall of the tokamak, we use this coil here, magnetic coil, and we have to drive this magnetic coil to maintain the plasma and never touch the wall. So experiments have been done to use reinforcement learning to control this magnetic coil to avoid the plasma to touch the wall of the tokamak. Another use of reinforcement learning is robotic manipulation. Here we want to grasp different kinds of objects with a robot and a gripper. So the input of the system is the image from the camera here, camera above the robot, and the output, the expected output, is the move of the arm, the robot arm, and the move of the gripper to open or close the gripper. To perform this task with reinforcement learning, the robot makes all the robots make some experiments. So just you see on this video, they try to grasp objects, to randomly try to grasp objects and learn by these experiments the good configuration for the gripper to be able to grasp different kinds of objects. So here you can see that they use 7 robots during 800 hours, so it's about 4 months, and they perform about more than 500,000 experiments. But at the end, they succeed to grasp not every time, but in 86% of the attempt of the grasp were successful to grasp unseen objects. With unseen objects, it means that it was objects which were not present during the training. So, what is the main idea of reinforcement learning? The idea for this is that we have a system, we call it an agent. The goal of the agent is to learn something, to learn a task. For example, for the robot, to learn to grasp the different objects. So it has to do something. So this agent will need to learn its task, and to learn its task, it needs some data, just like for supervised learning or unsupervised learning. But contrary to the supervised learning or unsupervised learning, the data used for learning are not provided by the human, but the system will get its own learning data. How does it do that? It does that by performing some action on its environment. Which means that, for example, the robot will move and try to grasp an object randomly. So this is an action. When the agent performs an action on its environment, this environment will change. So we have a new state, which is the state is all the information from the new environment, which are described by the state, and it's very important, it will receive a reward. The reward is a positive or negative number, and it reflects if this action was a good action By good, I mean an action which corresponds to what was expected by this agent to do. For example, for the robot, if it succeeds in grasping the object, we will give the agent a positive reward to indicate that this action was what we expected the agent to do. But if the robot, for example, fails to grasp the object, it will receive a negative reward, which indicates that we are not happy with this action, with the result of this action. And the goal of reinforcement learning is to, for an agent to learn, to act, to perform different actions on its environment, to maximize the sum of long-term rewards. So, what is long-term rewards? It's the sum of all the rewards from now to the end of the action. So for a system which learn with reinforcement learning, training consists in searching for what we call an optimal policy. So what is a policy? Policy is a kind of, just like a function, which take as input a state of the environment, so all information from the environment, and from this information of the environment, the policy will decide which is the best action to perform on this environment to get a positive reward. So, for example, let's take an example here. We have an agent on the environment. On this environment, we have a robot, humanoid robot, and the goal for the agent is to learn to control the robot, for the robot to be able to walk. Okay, so we want to learn the robot to walk. So the agent will perform some action. This action consists on driving the different motors of the articulation of the robot. And of course, because we do this, the robot will change its position on this environment. So we will measure with observations different parameters of the robot. The robot joints, the angle between this articulation and this articulation here, the acceleration of the robot, the velocity of the robot, all the sensors of the robot, for example, the camera vision, we will get all this information. This is what we call observations. And a reward. For example, because we want the robot to walk, if the robot manages to walk few centimeters, we will give a positive reward. But after this action, if the robot falls down, we will send a negative reward. Okay, so the system, the agent, will, after its action, will receive a reward and observation of the new state. Both reward and observation will be used by the reinforcement learning algorithm, will be used to update the policy function for the next time to be able to predict a new action. And with this observation as input to the policy function, we will generate the next action to perform by the robot to be able to continue to learn walking. So in resume, the agent is a software that generate actions on which update the policy to, at the end, produce the best long-term reward. So here the reward, the total reward will be, for example, each meter the robot walks we will receive a positive reward. And if it walks 10 meters, we will receive a big reward to reward the robot to have been able to walk so long time. The environment is everything else, the agents. So the environment is where actions are sent. Look here, for example, the environment is a robot, but the robot plus obstacles, plus the ground, plus different things. And the environment provides reward on observation to the agent. So we have two kinds of reinforcement learning model. We have some which are qualified as model-based or model-free. So model-free reinforcement learning is when the agent, which try to learn, when the agent doesn't know anything about the environment. For example, if we have an agent which try to drive an autonomous car, model-free means that it doesn't have, for example, a plan of the road. So, because the agent has to perform some action, for example, decide here if it continue to drive forward, turn on the left, or turn on the right. It has the three choice. Because it doesn't have a plan, the map of the road, it doesn't know that it's stupid to turn on the right. So it will test all the possibilities. Continue forward, continue on the left, or continue on the right. But when it will go on the right, it will receive a negative reward because it's out of the road. Maybe there is a wall here, and the car will crash. So a model-free reinforcement learning, because it doesn't know anything about its environment, it is a more general case. You don't have to give information. So it's model-free reinforcement learning will work for every kind of problem. But the problem is that because you don't have information about the model, you must explore even some stupid action. Donc, it's a waste of time. On the opposite, we have a model-based reinforcement learning. So here we have some knowledge about the environment. For example, we have a map of the road. So we know here, when we have to decide the next action, we know here that one possible action is to turn on the left or to continue forward, but we know that it's not possible to turn on the right because there is no road or maybe a wall, so it's a waste of time to try this solution, this action. So with this, we avoid exploration of low reward areas. So we will save time, but the problem is that we must give a model. Yes, we must give a model to this reinforcement learning algorithm. So we have to build this map, for example. Okay, so there is two types of reinforcement learning techniques. We can use a simulated environment or real environment. With real environment, it's the more realistic because at the end, the system will have to work on a real environment. So if we train on the real environment, it's perfect. It corresponds to the goal. So we will have a better accuracy. But advantage too. Another advantage is you don't have to, if you want to simulate something, you have to make a model. So here, if you directly work on the real environment, you don't have to build a model. So you save some time. On the opposite, if you first use a simulated model to train your agent before finishing the training on the real environment, you can do something more speed because more quickly. On the opposite, instead of directly learn the system on real environment, you can first use a simulated environment to start the learning process. Then when the learning process is in good condition, you can finish the learning process in reality. So you have to make a model. You will lose a bit of time to make a model, but you have some advantage. One of the advantages of using a simulated environment to start the learning of the process, the learning of the agent, is that for example, you can accelerate the learning process because with a simulator, you can accelerate all the movement, which is not possible with a real system. And you can parallelize too. You can do it on many computers at the same time. On each computer will perform an action, just you have seen with 7 robots on the example before. Having 7 real robots, it's costly. You have to pay a lot to buy 7 robots, but having 7 robots in simulation is less costly. Another advantage of using simulated environment is that you can easily change the condition. For example, if you use reinforcement learning with a simulator to learn the system for driving a car, you can change the lighting condition. For example, you can simulate night, foggy day, a day when it rains with the sun and so on. You can change the meteorological condition. You can change the surface. You can put ice to see how the car will react when it drives on ice, even if you perform the test during summer. It's not a problem to simulate ice. And you can, at the beginning, the system, when it starts learning, it will do some action very stupidly. For example, try with a car, try to turn on the left, maybe on the left there is a wall, so the car will bump into the wall. But if it's with a simulator, it's not important. It's not there's no problem if the car bump into the wall with a simulator. But of course, with a real system, the driver may be damaged, and it costs a lot to change a car each time the system performs a bad action. Okay, let's talk about reward. So reward is a function which provides a number, positive, negative, or null, based on action performed by the agent on the environment and the current state. The goal of reinforcement learning is to maximize the accumulated reward. So we want, at the end, to have at the end of the episode to have the maximum accumulated reward. So the reinforcement learning takes a lot of time to converge if reward is too sparse. What does it mean? For example, if we want a robot, humanoid robot, if we want it to learn to walk, and if we give a reward only when it walks 10 meters, a big reward, but if it needs to walk 10 meters, it's too sparse because it has to coordinate the movement of all its motors, which is something quite difficult, during 10 meters to get the reward. So this is what we call too sparse reward. So the solution is to provide small rewards, intermediate rewards for the robot. For example, each meter we give the robot a small reward. So the robot will take an action to get this reward, then an action to get this reward, and so on. So it will be guided more quickly to the good coordination of its motor to get this small reward instead of getting this faraway reward. But the solution has to be carefully designed. For example, if the reward is only for the robot here after 1 meter, the robot may fall down because it falls down here, so it will receive this reward because the robot is here. So this is not what we want the robot to do. We want it to be here, but standing up, not being on the floor. So the good solution is to give it the reward if the robot is here, and the gravity center of the robot, for example, is higher than, let's say, 1 meter, which is the reflect of the fact that the robot is standing up and not on the ground. So this is why we say this reward has to be carefully designed, because we must specify a lot of conditions for the robot to get this reward, to be here and standing up. So the design of the reward is the reward function is something which is difficult and has to be done iteratively. If we realize that the robot falls down on a crawl instead of walking to get the next reward, we must modify the reward function to oblige the robot to be here, but not on the ground. Okay, so with reinforcement learning, we have two concepts, which is exploration and exploitation. Each time the robot performs some actions, it gives the robot, it gives the system, the agent, new experiences. An experience is a new state, observation, which is a reflect of the new state, and a reward. And this is all this experience which will be used for learning the optimal policy. So to get these experiences, we have to perform some actions. And there are two ways to decide which action to perform. The first one, exploration. Exploration is when you select from all the possible actions, you select randomly which action to perform. Okay, so you select a new action randomly, so you test something, you get a new experience, but because you test it randomly, maybe this action will lead to a poor reward. Okay. On the opposite, you have the exploitation. Exploitation is when you, instead of selecting a reward randomly, you select the reward which you think has, at this moment, the best reward, the best possible reward among all the possible actions. But the problem is maybe there are another action which can lead to a better reward, but you don't know. Let's see this on this example. For example, you have the agent on the state S4, and it has here two possibilities, two possible actions: to go on the left or to go on the right. If it goes on the left, it will change from state S4 to the state S3 and receive a positive reward of +1. If it decides to choose the action go to the right, it will change to the state S5 and receive a reward -1. So if we do exploitation, we can decide to go on the left because the reward here is better than this reward here. But next, we have, when we will be on this place, we have only the choice to go on the left or to go on the right. So here, the reward is only 0. So you don't gain a lot of things here. But for example, if you decide to go on the right, you receive, yes, not a good reward, -1, but maybe the next time, if you decide to go to the right, you may receive, for example, here, a reward of, let's say, +10, for example. So, using exploitation leads to go to the left, but maybe it's not the best solution. Maybe another action, this one, can lead to a better reward because it can go to a better solution here. So, how do we decide if at a moment the agent use exploration, random actions, or exploitation, the current best rewarded action? We can use for this what we call epsilon greedy strategy. So with the epsilon greedy strategy, we have a small epsilon here, something lower than 1, but with a high value, just like 0.9. This is the initial value for epsilon. And we will decrease the value of epsilon, for example, 0.1, and we will decrease this for each episode, each steps during the training, we will decrease the epsilon. And after a certain step here, we have a minimum epsilon, and here we stop decreasing epsilon. So here is the plot for the epsilon decrease. And how do we use this epsilon? Imagine you are on the step 100, for example. Here, you randomly generate a number between 0 and 1, and if this number is lower than this point, it's something like 0.6, for example, if it's under, if the value is under this value here, the value of epsilon, so we will do exploration. If it's upper than this value, we will do exploitation. So with the epsilon greedy strategy, you see that at the beginning, you have more chance to do exploration rather than to do exploitation. And it's normal because at the beginning we have no knowledge about the environment, so we can only do random actions. But after a moment, because we get more and more experiences, we have enough experiences to train our model, to have a good knowledge about the environment or about how to get a good reward. So after a few moments, we will privilege, we'll mostly use exploitation rather than exploration. So this is about the same if you, for example, you go to an unknown city and you want to eat in a restaurant every night. So at the beginning, because you don't know which restaurant is good, you randomly go to a different restaurant each day. But after a few days, you finish by learning that on this restaurant the meat is good, and on this one it's not very good. So after a few days, you will do exploitation. You will exploit your knowledge about which restaurant is good and which one is not good, to go to the best restaurant based on your current knowledge. But you continue sometimes to go to random restaurant.